Good afternoon, everybody, and welcome to this event. Today we have a special guest, Valerio Velardo, who is an expert on the topic of machine learning applied to the audio and music field. Thank you, Valerio, for being with us today.
Yeah, thank you,
Valerio.
Luigi.
Thank you. Valerio has a strong background on both music and technology. In fact, together with several conservatory diplomas, he also attended a PhD program in artificial intelligence music after the degree in astrophysics. Now he is a very active and important figure of his kind, works as a researcher and consultant for many startups and companies, and he has recently founded a worldwide community of researchers and enthusiasts on music artificial intelligence. If you want to check it out, it's called The Sound of AI. Now, I won't steal you any more time, and I leave the floor to you, Valerio. I will come back at the end for reading the questions you guys want to ask him on the chat. Thank you and see you later.
Okay, great. Thanks a lot, Luigi, for the presentation and for the invitation here. Yeah, it's a pleasure to be here and just like spread some like knowledge and stuff like about like generative music and AI music more in general. Cool. So I'm going to share my screen, and yeah, because I have a presentation. So yeah, Luigi, could you please let me know if you can see my screen?
Yes, I can.
Okay, yeah, that's great. Okay, so I'll just start the presentation over here.
Okay.
Okay, cool. So the title of the presentation is Generating Music with Artificial Intelligence, and we're going to be looking at the history of AI music generation, some of the challenges that we have, and future prospects. So a little bit about myself. So as Luigi was mentioning, so I'm an AI audio music consultant, and I founded like this YouTube channel, and you'll know a little more about that like towards the end of this presentation. That's called The Sound of AI, and along with the YouTube channel, there's also a Slack community, and a community that's quite active where we have like people who are interested in all things AI, audio, and music. My background comes from two worlds, really. So one is as a musician, and still today I define myself as a musician first. So I studied like piano, performance, music composition, conducting, but I've also studied physics, and I've always been interested in programming. I've been programming since I was a teen, and I also have always been interested in artificial intelligence. And so I decided to combine these two passions of mine, and I believe like this is one of the things that many people who are in generative music actually do. So they come from both a scientific programming world and a musical one. And so I did this PhD in the UK. And I also founded a company, Moderator, and of course, it's in generative music, AI music stuff, and you'll know a little bit more about that during this presentation. Okay, so this is a little bit of an overview of the different points that I'll be touching upon today. So initially, we'll start from the difference between intelligent and creative tasks. Then we'll ask ourselves, what's generative music? So how can we define different types of generative music systems? And then I'm going to give you guys a brief history of generative music. So some of the milestones that we've reached and different phases in generative music, if you will. And then in the process, also share some example of generative music systems, or in other words, systems that can generate music more or less autonomously. And then we'll just move on to an interesting topic, which is that of the impact of generative music on the music industry and the entertainment industry as well, a kind of like larger perspective. And finally, I just want to give you like or leave you with a few questions that you can ask yourself to understand whether generative music could be something that you may be interested in pursuing. Okay, so without any further ado, let's get started. And so, first thing first, so the difference between intelligence and creative tasks. So I'm quite sure that many of the people in the audience would know where this place is, and it's in Rome. And here, what we are attempting to do, it's kind of like some sort of like object identification, right? And this is like a quite important kind of a task that we have in image processing. And this process of image detection or image recognition, or object detection, I should say in this case, is quite similar in a sense to this other task that we have here. Of course, this is just like very, so we don't have like the task itself, but you can imagine that here we have an AI system that tries to understand whether like this robot has an anomaly or not. And this task is also similar to this other task, which is speech recognition. So all of you guys who have like an Android phone, for example, would have a speech recognition system that works reasonably well. It's not perfect, but it works reasonably well. But why am I saying that all of these tasks are somewhat similar? Well, so we have speech recognition, we have object detection, and we have anomaly detection. Well, all of them, in a sense, have a kind of objective success metric. So we have a way of deciding whether or not we've been successful with this task itself. So we have, when we do speech recognition, of course, the kind of baseline is the speech that people are uttering, producing. And so there's a level of objectivity there. So you can tell whether the system is succeeding or if it's failing. Same thing with object detection. Of course, you may have some kind of like edge cases where it's very difficult to identify an object, even for a human being. But most of the time, objects are quite objectively understandable, at least for us human beings. And same thing for anomaly detection. So either you have an anomaly or you don't have it. Okay, I know I'm kind of like simplifying the matter, but you can think of it this way. Now, the other thing that makes all of these tasks quite similar is that these are all well-defined problems. So we have a clear description, and we can create a description of this problem or problem space that's well-defined. We can formalize it. Okay, so now let's think about other types of tasks. For example, performing a symphony, right? Or creating a symphony, or creating a painting. So in this case, we have a problem. First of all, we really don't have an objective success metric. So what's a successful painting? Or what's a successful piece of music? This is very subjective stuff. So it's very difficult to come up with a metric that we can use to decide whether a piece of art, a creative piece, is successful or not. And it may well be that I love certain type of music. So for example, I'm into contemporary classical music, and I love a composer like Messiaen. But many people who listen to the same music and say, well, this is really, really bad music. I don't like it. And there's nothing wrong. And the reason why this happens is because we don't have an objective success metric, because the success metric, if you will, is subjective. And then at the same time, we don't have a definition of the problem space that could be formalized. So the problem itself, music, painting, literature, are not well-defined spaces, right? Because there's a lot of ambiguity, there's a lot of complexity in music that's very difficult to capture in a formal way. And that's not only true for music, but also for other creative tasks like writing or painting, or even making jokes. Cool. So now, the first tasks that we saw belong to what we call artificial intelligence. One way or another, it's one subfield or another. It could be speech processing, it could be image processing, or like anomaly detection, but all of them, you can be called one way or another artificial intelligence. Now, the tasks which belong to the second typology that I discussed earlier, so painting and composing or performing, belong to what we call computational creativity. Now, what's computational creativity? Well, computational creativity is the art and science of generating or producing systems that can create creative artifacts, like a painting or a piece of music. Now, this, I'm very, very attached to this photo, well, not this picture in particular, but to this building, I should say, because I spent a lot of time in that tiny window there. That's the PhD graduate room at the University of Huddersfield, where I did my PhD, in fact. And in that room, as I said, I was spending a lot of time asking mainly these questions here. So, can machines be creative? Can I reproduce through coding how humans compose music? And how can we formalize the compositional process? And for 3.5 years, as I said, I just like sat in that room and thought about these questions quite a lot and produced some research in this space. Now, so this is why and when I got in touch with generative music. So if you guys are not familiar with this term, generative music is a subfield of computational creativity. And of course, it focuses on music, and specifically on the generation of music. In other words, what we do in generative music is building creative music systems that can generate music by themselves. We'll see that there are different degrees of kind of like autonomous composition that we can have for different purposes, but the basic idea is this. You are a programmer, a generative music programmer. You create these systems and they generate music for you one way or another. Now, there are many ways of calling generative music. So this field has a gazillion names. You may have heard algorithmic composition, AI music creativity, procedural music, or musical meta creation. So all of these names are different flavors, if you will, of the very same thing, which is generative music. At the end of the day, we want to generate music using some algorithms and having machines thinking musically, if you will. Okay, so now, what are some of the challenges that we have in generative music? And as I said, these challenges derive directly from those two issues, that we don't have an objective way of representing success for a musical piece, and the fact that we have also a lot of problems in formalizing music. And so here, I just listed 3 questions that are still very, very open and open to research, I should say. So how can we define or represent music? This is a very difficult problem, and it's still completely unsolved. And I bet it will remain as such for a very, very long time. And then once we have a generative music, how can we evaluate this generative music and itself, the music that is generated? So how can we say when this piece of music is good or bad? And connected to that, who should evaluate generative music? Is it normal people, the lay person, or is it music professionals, or perhaps music students, or perhaps generative music researchers themselves? So we still don't know. There's still a lot that we don't know about all of these questions. Now, the interesting aspect of generative music, and it's one of the reasons I love it so much, is that this is a highly interdisciplinary field. The generative music is connected with all of these other fields. Of course, with artificial intelligence, we would borrow a lot of techniques from artificial intelligence to create these generative music systems, as we'll see in a few slides. Also, there's a connection between generative music and music information retrieval, or MIR. Now, I'm sure many of you guys are already familiar with MIR, but in a nutshell, MIR is kind of like the reverse side of the very same kind of generative music. In MIR, we use artificial intelligence and all the other algorithmic digital signal processing techniques to analyze music, to extract information from music, like, for example, genre, mood, chord progressions. And these two kind of fields are somewhat connected, because in order to generate music, you need to understand it first. You need to have the capacity to process it and to understand all of its building blocks. Then generative music is somewhat connected to digital signal processing, or more specifically, audio DSP, because we may use a lot of like audio representations for generating music, and you need to be very well versed in digital signal processing to understand how to generate music directly from audio. And that generative music is definitely connected with software engineering. So we don't just want to build a system in a very scrappy way. We want also to build products. And for building products, we need to know about software engineering, DevOps, MLOps, and all of this kind of stuff. But generative music is also connected to more abstract disciplines, if you will, like music cognition. We want to learn how humans perceive music in order to create systems that generate music the best way possible, the most meaningful way possible. And of course, generative music is connected with music theory and computational musicology. And because we need to understand music in order to let computers create music by themselves. And this is one of the reasons why I love generative music so much, because it has so many of the different things that I've studied in my life. And I can experiment and be one day a music theorist, the day after an AI researcher, and the third day of the week, I can be a software engineer. And I love it, really. Now, I want to give you a way of classifying different generative music systems. So for that, I'm going to give you like a few questions that you can ask yourself to create this classification. So what's the goal of the system? Now, we may have a generative music system that generates melodies, another one that generates chord sequences or full tracks. And right now, these are getting like all the hype. Or for creating jazz improvisation, or generating a series of loops, or perhaps generating counterpoint. But the goal of the system can also be thought in the sense of the end goal. So what's the end goal, the musical end goal of the system? So this music can be created for video games, or for movies, or perhaps for ads, or it's just concert music or absolute music that doesn't need any attachment to any other digital media or analog media for that matter. Now, another way of classifying a system is by asking who uses the system. And here we have a lot of answers. So we might create a system that is necessary for composers, just for example, to get some inspiration or to co-compose music, or for developers, because they may want to have a very simple API, well, not simple, because under the hood there's a lot of complexity, but they may have a simple API to get music that they may serve to their users, end users. Or this system could be for researchers, for example, for musicologists to understand the possibilities of music creation, or for consumers directly, right? For example, imagine you have an app that generates music for TikTok consumers, right? Or for songwriters. Songwriters write the lyrics, and then they have a system, a companion system that generates the music based off the lyrics that they wrote. Sorry, just needed a sip of water. Okay, but there are also a couple of questions that we may ask for classifying generative music system. So how is music represented? How is music generated? So as for music representation, in generative music, well, not just generative music, but also music informatics and, if you will, music information retrieval, we mainly have two types of representation. One is called symbolic, and the other one is raw audio. Let's start with symbolic first. So here you have an example of symbolic music representation, and a lot of kudos to you guys if you guess where does like this music excerpt comes from. Okay, so just to talk about symbolic music representation, well, here the idea is that you have symbols that represent musical events. And this is like the most, not necessarily basic, but I would say like the most common way of representing music, at least in Western countries, through a score like this. Now you have different types of ways of representing music symbolically. For example, piano rolls. And those of you who are producers may be very familiar with the piano roll. So here, this is an XY kind of diagram, if you will. On the x-axis, you have time, and on the y-axis, you have pitch. And each point, each dot in this diagram corresponds to a musical event with a certain pitch and certain length in time. But then we also have other formats, for example, MIDI, which is overwhelmingly famous and used, but also music XML that's also getting like some traction lately. But then we have another way of representing music, which is the raw audio representation. And this is basically taking a waveform and using it directly for representing music. This is basically a waveform associated to a wave file, directly like that. Cool. So now, how does symbolic music generation work? Well, from a very, very high point of view, it works like this. You have some music, symbolic music, you may train a machine learning model like this, and then the machine learning model creates other music or symbolic music as an output. Now, this is only like one subcase of the different music generation systems that we have that uses machine learning. As we'll see in a second, there are a bunch of other techniques that we may use. But nowadays, a lot of generative music systems rely on machine learning. So we have like some training data or symbolically represented music that gets fed into the network or whatever other machine learning algorithm, and then get as an output generation of new music, hopefully interesting music. Now, in the case of raw audio music generation, the situation is a bit different. So we don't pass through the symbolic representation, but we directly use raw audio. So we pass in a lot of wave files, which represent our music, to a network, and then the network hopefully will be able to generate directly music in the raw audio environment domain directly. So these are like the two main big kind of like subcategories of generative music representation. Okay, so now let's take a look at the different techniques that we can use to generate music. And here, it you really have the whole AI algorithmic spectrum. So we can use symbolic AI, so expert systems, or generative grammars. All of these kind of things can be used, or rule-based systems for generating music, and they have been used. Then, of course, we can use machine learning or deep learning. So all sorts of algorithms have been used here, but mainly over the last few years, the focus has been on deep learning and neural networks, different architectures, from variational autoencoders to GANs to LSTM networks to CNN even. Statistical methods, for example, hidden Markov models or other methods have been used to generate all sorts of music, but also more algorithmic methods, like, for example, using fractals for generating music or cellular automata, and even evolutionary algorithms. And here, the issue is defining, so I don't know if you guys are familiar with the concept of genetic algorithms, but there you need to have kind of a fitness function that says whether like the music that the item that you've generated, in our case music, is good or it is not, or how good it is. And well, there we have an issue because we don't know what makes good music. So that is like an interesting spin. Once again, seeing the problem of the kind of subjectivity of music generation or music composition in general, and then seeing how that impacts different algorithms that have been successfully used in artificial intelligence in a gazillion different fields. And this is the case of generative revolutionary algorithms. Now, of course, I don't have the time to go through all of this methods like one by one, and you can refer to this couple of papers which are fantastic. So the one on the left is more focused on traditional algorithmic methods, whereas the one on the right focuses more on deep learning techniques and neural network architectures. Now, let me move on to the history of generative music. Now that you guys have more or less an idea of where like we are, the kind of boundaries of this field. So you can say that we have initial so-called phase that I would call academic niche that goes from the 50s to 2010. That I would call the academic niche. Then from 2010 onwards, we are entering the phase of generative music startups. And after 2016, we're entering the phase of big tech. Now, let's break these ones down one by one. So the academic niche, so from the 50s to 2010. So here we had a lot of experimentation, but the advancements were very incremental, little advancements. And you would rarely get a full piece of music, but rather you would get, for example, a melody generated or chord progression or improvisation, stuff like that. But rarely you get a full piece generated. And the focus wasn't necessarily on audio production quality, but just on the composition itself. And most of the time in the academic niche phase, people would focus on symbolic music generation. And the community itself was quite scattered. You would have people from computer science working on this, people from music theory, but with some computational skills, people from music cognition. So from all over the place, really, and there wasn't really a united community. Now, you may be surprised by this, but the first attempt at generating music with computers came already in 1956, and this was called the Iliac Switch, and this is a quartet, string quartet with different movements. And let's just listen to a little bit of this. It's in a contemporary style. Okay, you get the idea. So this was the first piece of music generated by a computer that we are aware of. Quite impressive for 1956. Now, let's move on. I want to give you another example of this phase with a quite famous generative music piece of software called the Moderator, built by Pache, who's one of the leading scientists in generative music. So here, the system is able to understand what a performer plays and then responding in a sort of question-answer conversation, musical conversation. This is Pache. It's quite interesting how Moderator really is able to pick up the style of the piece and reproduce it and create variation. So it's very, very interesting application of this one. Okay, and then in 2015, as part of my PhD thesis, I came up with this system that I called S, which stands for Simulation of Society of Songwriters. So here you should think of this system as a multi-agent system where you have a bunch of agents which compose and share music. They compose rock music and they can share it. But the cool thing here is that each rock music agent can evolve its compositional style based on the pressure, social pressure coming from other music or musicians. So each agent generates music, it shares it, and it listens to the music generated by other agents. And then based on its own musical taste, it decides what to pick from other agents' styles. Cool. Now, let's move on to the second phase, which I would call generative music startups. And this, I would say, started around 2010. In the generative music startup phase, you have a lot of focus this time, of course, on product, because we are talking about startup companies which want to build products. And the focus shifted from scattered or kind of like smaller tasks, like generating melody or generating chord sequences, towards full piece generation. And here we started to have first high quality generative music data sets compiled by these companies, which would then use machine learning for their systems. Here we have a bunch of these companies. So the one that I created and then sold, Melodrive, and then we have a bunch of others, JukeDeck, Amper Music, Endel, Rupert, and many more. Now, I'm just going to give you an example of what we did at Melodrive, and we started Melodrive in 2016. So we basically built a real-time video game music generation engine. So basically what this was an engine that could generate music in real time while you play a game, and the music has the ability to adapt itself to the emotional context of a video game. So for example, if you get attacked by an enemy, the music would ramp up and become more dramatic. And whereas like if you're just chilling out on a beach, then the music would be like very mellow and soft. Now, we released the Melodrive engine as an SDK for the Unity game engine, and this Melodrive was used by many indie game developers. Now, one thing that I want to share with you guys is kind of like artifacts that we created at Melodrive that's called Counter. So this is a kind of like artistic virtual reality experience. So you have this audiovisual, evolving, ever-changing landscapes with multiple paintings and paintings in paintings, and you have portals. So when you get, like, for example, to this painting in the painting, you can get in there and be transposed to this other painting. And all of this, of course, was inspired by the work of Vasily Kandinsky, as you can guess from here. Now, unfortunately, I don't have a video for this, but here we just released the soundtrack. And this was generated like using some artificial intelligence. So here you have an example. Okay, so you get an idea. Of course, here we just linearized the pieces, but these were like spatialized in the VR application, and then like the whole piece, like the kind of like the generation was dynamic, and people could, while like wandering like in this virtual environments, could experience the music in a dynamic way. Okay, now let's move on to big tech. So what about big tech? So here, from 2016, I have to say, we see big tech giants that entered the game, if you will. So the focus was on that they have so far was on deep learning, with massive data sets, massive computational power, massive neural network architectures. Now, for them, there hasn't been so far any commercial end goal, or at least now, but rather they would use generative music as a kind of playground to see how much they could push ahead creative AI, right? And seeing how creativity can be captured using algorithms and artificial intelligence. Now, here we have a few different examples like of big tech companies that worked in this space. Magenta, which is a project inside Google, and OpenAI, Amazon, IBM, Watson. So at Magenta, they developed a lot of very interesting cool tools that can be used by music producers directly. One of these is called the Music BAE, or Music Variational Autoencoder. And here you see like how the Music BAE is capable of like moving from one loop to another loop in a kind of like seamless way. So this is the first loop, second loop, Now listen to the transition and how smoothly it is. Here we are back at the beginning. So yeah, quite impressive work by the guys at Google, not surprisingly. So then we have from Amazon in 2019, AWS Deep Composer. So they released this neural network that allows like machine learning engineers like to just like play around with music. And one thing that they also sold was this like little keyboard or hardware. So in this case, like the end goal of this product wasn't really like for consumers, but rather for machine learning engineers and showing the different capabilities that are out there with machine learning and creativity. And then we have a very impressive result by the guys at OpenAI. So the model that they built was Jukebox. So this is directly raw audio generation. And they used a vector quantized or VQ variational autoencoder. And this is really impressive stuff, as you'll hear in a second. So they were able to generate lead vocals and to produce directly performance details. And this is the difference between symbolic music generation and raw audio generation, or at least one of the differences, that using raw audio generation, we can directly capture all of the timbral aspects and performance aspects that are lost in a symbolic representation, which is way more constrained or lower dimensional. And now let's listen to some of these examples at Jukebox. Okay, so I have one here that I really love, which is this classic pop by Frank Sinatra.
It's Christmas time. And you know what that means. Oh, it's hot like that. Yes, I like your tweet. This year it's Christmas time, and you know what that means. It's hot tub time.
It's impressive how good the music is and how good the voice of Frank Sinatra is created. Yeah, and let's listen to another example here real quick. For example, this one in the style of Simon and Garfunkel. Yeah, it's quite impressive. As you can hear, there's still a few artifacts here and there, but overall the result is mesmerizing. Okay, so now I want to add to this three steps or three phases, a new phase that I don't know if it's going to happen, but I'm really pushing for that to happen, which is the so-called open source phase, which I guess like it's actually started with Sound of the Eye community in 2020. So I'm currently working with the Sound of the Eye community on open source research. So this is a research project which is completely open source and crowdsourced. We have around 100+ people working to build in a fully distributed manner a machine learning powered synthesizer. And so we organize like this research project into multiple research groups which are working on individual components of the whole system, which, as I said, is this machine learning powered synthesizer. And let me show you a little bit of this. So by the way, this is the website of the project, which was created by the community itself. So here you can see like the different parts of this system. So here we have like text to sound. So basically the idea here is that you can ask the synthesizer what sound you want. For example, give me an aggressive guitar. And so we capture the voice, we record it, and we do text to speech, and then we pass that information over to this core component here that's production, where we have like the GUI and puts together all the other parts of it. And then based on that feedback, we generate a sound, a guitar sound, that in that case is an aggressive guitar sound. And then we have a sampler where you can use like your own keyboard to like, and you can't just like jump and use like the sounds that are generated by this synthesizer directly. So really like this open source approach to generative music research has a lot of value. A lot of people are learning a lot about the space, and then there's a lot of value like in bringing together people like from all over the world working on the same problem, coming from two very different backgrounds. And another thing that I think is also super cool is that we built this audio annotation tools, and we are building a data set here that we'll use for this ML synthesizer. And you can see it here. By the way, at the moment, we are trying to annotate as much as we can. So it would be fantastic if you guys could also help us create this data set, which, as you can see here, is a data set where like we just like play simple audio sample, a guitar audio sample, and then you can decide whether like this is bright or if it is dark, or how full or how hollow this sound is, and then you can submit it. And we're going to use all of this information then to generate guitar samples that kind of like resemble or can be described through like words and semantic tagging. Cool. So this is, again, like what I think like it's going to be the future of generative music research. And I think for that matter, of a lot of research, probably we're going to move towards more open source projects where the communities are going to source the data first, and then also create the research and software that are going to be used by the widest community. Okay, so now that you have an idea of the different phases that we have in generative music, let's take a look at the current challenges that we still have. Well, a big challenge is that we have problems with long-term structural music coherence. So the music that you've heard so far, generated by generative music systems, works quite well at kind of like a lower resolution, so where you are talking about like a musical phrase, a few bars, but then it's very difficult for these systems to create a direction, an overall direction and structure for a musical piece that may be convincing. Another big issue that we have at the moment is audio production quality. And the symbolic music generation systems can do a pretty good job at the compositional task, but then the audio rendering, if it's not humanly tweaked, humanly produced, it's not that great. And raw audio generation, as you've heard from Jukebox by OpenAI, is great, is good, but it's not great audio production quality-wise. And then another big problem is that now we have a lot of very cool tech, but still we really haven't turned that cool tech into viable products. We now have the tech, but we don't have products that people may necessarily want to use. Now, talking about people, consumers, and the impact of generative music on the music field, yeah, let's ask this question. So how's generative music transforming music? And who's generative music impacting? Well, I think generative music is really impacting three actors. It's going to impact, and it's already impacting, listeners, musicians, and media creators. Now let's take a look at each of these actors one at a time and then see how generative music can impact their connection and relationship with music. So let's focus on generative music and the impact it will have on listeners first. The basic idea here is that generative music is going to enhance the listening experience. So we have AI system, AI generative music systems that just generate the music, and the music is consumed by a listener directly. And a first example of this is the Elliott switch, and we already listened to that, the quartet, the string quartet that we heard earlier. Now, we have a bunch of companies that are focusing on this type of task. For example, emblem, that creates personalized sound environments that you can use to relax, sleep, or study, perhaps. And we also have artists who work in this space, so creating generative music systems that can be directly consumed by users or listeners. Bloom is an example of this, which was created by Ryan Eno and Peter Chilvers. This is a mobile app, and you can think of it as a generative music engine, or a music space that continuously evolves within certain musical constraints. And then the listener can explore these ever-changing musical worlds. Now, let's take a quick listen to this.
The original Bloom was have a sort of family resemblance to Bloom, but are different envelopes of possibilities, really, both sonically and visually.
You get the idea. Basically here, what Brian Eno is trying to do is creating this multisensorial experience where you have both visuals and music. And the music evolves over time in a kind of unpredictable way, but always within certain boundaries. And this is a way of changing the way we experience music. It's not going to be a linear experience anymore, but rather it's going to be a non-linear piece of music that's going to evolve by itself. Then another example in this category is The Pace, which was a project by Dua Lipa in partnership with Jaguar from 2018. Basically here, the idea was that Dua Lipa created this pop piece of music in which a lot of different remixes. And then the artificial intelligence behind the scenes was recombining these different parts of the song dynamically. And the remix was generated based on your musical profile or musical taste on Spotify. So you would go to this website, the Pace website, then you would connect to your Spotify, then your musical profile would be analyzed, and based on that, a remix would be created with certain instrumentation, a certain pace, which would actually reflect your own musical taste. And once again, here we are creating music that adapts to the needs of the listener. So what should we expect in the future from generative music, and how it's going to impact generative music to the listener? So I think what we're going to see is personalized functional music. So music based on mood, music based on the weather, for example. So depending on the mood you're in, a remix for the same song can change, and based also perhaps on the weather or your heart rate or stuff like that. And then we're also going to see interactive albums and songs, and I'm super excited to see this because since the start of the music competition, we've always listened to music in a kind of linear way. So we go to a piece of music and we know the beginning, we know the middle part and the end. And more or less it always sounds the same. But just like Brian Eno tried out, it's possible to have music that evolves all the time, and you can interact with the music, with an album, so that it responds to who you are, your musical taste, and what you are experiencing in that moment. Now let's take a look at the second aspect or actors that generative music is going to impact, and these are musicians. So, and here we're talking about AI-powered tools for musicians. And of course, here we are also experimenting with human-machine interaction, taking a look at different possible use cases. So we could have some of these AI-powered tools for musicians that can help songwriters or composers or inspire them, for example. If you're stuck with a musical idea and you need some inspiration, perhaps you can pair with one of these AI-powered tools for musicians, or they can enhance you. What does this mean? It means that they can perhaps create an infinite version of yourself within a non-linear piece of media, like, for example, a video game or a virtual reality experience. They can also facilitate music, practicing music or collaboration. So you can collaborate with this music AI-powered tools for musicians, for example, to create music together. You can practice with them, or you can use them also for education. Imagine you have a piece of AI music software that generates exercises that people can, or pupils, music students can use to practice their performing skills. And these exercises are created based on the user's weaknesses and strengths. Now, here's an example of kind of human-machine collaboration. And this is Shimon. It's a jazz improviser, and I just want to let you take a look at this. It's super cool. So this is super cool. Shimon understands what you are playing, and then it kind of improvises with you, which is really, really cool. Now, imagine if you had the same thing, but with a, I don't know, like you may be improvising or just playing with a virtual copy of Jimi Hendrix, or I don't know, with a famous musician, a bassist. And so you are a drummer and you want to play bass, or just like jam together with a very famous bass player, and you could do that in the future. Now, another interesting AI-powered tool for musician comes from Magenta Studio. Once again, the guys at Google. So they released these plugins which go in Ableton. One is called Continue, then you have Groove, Generate for Bass, Drumify, and Interpolate. And they all do slightly different things. For example, with Continue, you can upload a piece of music that you created, and then Continue, just the words say, will continue what you created, will continue your melody. So you can use this for inspiration for facilitating your compositional process. Drumify is also like a really cool plugin. So you upload a melody or a chord progression or a bass line, and then Drumify will add a drum beat to it. And another really cool tool that the guys at Magenta built is MSynth, which is a synthesizer, machine learning synthesizer. And take a look at this because it's quite cool. You can think of this as a kind of like temporal space, and then you can move in this temporal space and have different sounds that merge together different voices. For example, the voice of a flute with that of a, I don't know, with that of a bass or stuff like that. And the sounds that come out are super weird and super interesting as well. So these are a lot of like possibilities for musicians to thrive on. Okay, so what should we expect in the future for this type of application of generative music, specifically the impact of generative music on musicians? So musicians will focus on high-level musical ideas, I do believe, whereas the details may be filled in by the artificial intelligence itself. So the boring computational processes will be offloaded to AI music tools. You can think of like also AI music buddies to practice and perform with. For example, your virtual Jimi Hendrix or your virtual David Gilmour, if you will. And I'm excited about this when composers will collaborate with AI tools to be more productive and to get inspiration. So there's a lot of jobs that are kind of like not super great, like for composers. For example, writing music for ads, that's quite boring most of the time. And so composers can really streamline the process of relying on artificial intelligence. And of course, they can also use artificial intelligence to get inspiration. Now, the third and final actors are media creators. So let's see how generative music is going to impact them. So AI tools will generate music media. So we have two types of media here. So linear media and interactive media. So when we think of linear media, we think of videos, movies, ads most of the time. For interactive media here, I'm referring to video games, virtual reality, augmented reality experiences, mixed reality experiences, and apps. Now, there's already quite a few companies, like for example, Amper Music, that allow you to generate music for videos. But I think like the most exciting part is that of using artificial intelligence to generate music for nonlinear media. So I think like that in the future, we'll see AI that will take over composition of music for videos and apps. Because as I said, this is like quite boring stuff. We don't need music that's the best music ever. Of course, I'm not talking about top-notch films and movies here. I'm talking about simple YouTube videos, and you need a very simple soundtrack there. And same thing for apps. But here, probably like this music will be potentially taken over by AI composition. But the most exciting part, as I was mentioning earlier, is that AI will enhance composers scoring interactive media. For example, for video games, VR, AR. And here, the use case is super clear. So whenever you're, for example, like playing a very long, very involved fantasy game, say for example, Skyrim, you have hundreds of hours of gameplay, but the music, of course, can only get you that much. And the music can be like 2 hour, 3 hour, 4 hour soundtrack, but it can be 100, 200 hour soundtrack. And then the music will never follow your steps in the game fully. So the opportunity here is that the composer will just create the script, the musical script for the music, and then the AI will get that musical script and implement it directly in the game, so that it will be able to take, like, for example, the very same musical idea and implement it in a very rushed way, or in a very dramatic way, or in a very relaxed way, depending on how you are, or where you are in the game and what you are experiencing. And finally, I can think also of AI-generated music for social media. For example, I want some music for my TikToks or Instagram stories and stuff like that. And this is going to be also a big one. Okay, all of this is great, but still we have a lot of music blockers, or generative music blockers. In other words, blockers that are impeding us to have generative music systems fully functional on many of these use cases that we discussed so far. And this is for a few reasons, a few blockers. First, music quality. Music quality is not at par with human music. And end users don't care who created the music, they just care about the quality of the music. And the quality of the music is not there from generative music systems yet. Then there's a lot of suspicion from markets and people, and there's a lot of inertia to change. And I saw this so well when I was working for Melodrive, when we were trying to innovate in the way that people would create video game music. And there, they have a tradition of years and years and years doing music in the very same way. And so just knocking at their door and saying, hey, from today, you can use generative music to streamline many of the things that you've been doing this way for 20 years. And then you can also add this extra level of adaptivity to it. Doesn't work. there's a lot of suspicion. So it's going to take some time before many of these industries will catch up to these news and updates that we have from technology. But in the end, the promise that we have from generative music, I think, are these two. Generative music will enable us to democratize music creation, that everyone will be able to be a musician. But do I mean by this that we are going to replace musicians? Of course not. The same way that Instagram hasn't got rid of photographers. We still have top-notch photographers, but at the same time, we have a lot of people who can play around with photography thanks to Instagram filters and Instagram and share what they've done, right? There's always going to be a place for top-notch photographers, and in the same way, there's always going to be a space, a room for very good musicians and composers, but people will be able to express themselves musically using AI in generative music systems. And at the same time, I think like the other big promise is that of extending musicians' capabilities. So for example, what I mentioned earlier, this ability to put extra powers to composers, enable them to create an infinite version of themselves, which can be in a game and score music in real time. That could be in a video game, but it could also be in an application or in a virtual reality environment. In the end, guys, like I want to leave you like with this final thing that for me, I think it's central. So generative music should extend what's musically possible, but it shouldn't replace what humans can do already. We have millions of musicians and we have fantastic linear music and music in general. We don't want to replace them. We just want to give new possibilities to music consumers as well as to musicians. The final thing that I want to touch upon, and I promise like I will touch it like at the end of this presentation, is this question. So, is generative music right for you? And to know whether this field is right for you, you should ask yourself these questions. Do you love interdisciplinary research? Do you love audio music above all else? Do you feel at home with fuzzy, ill-defined problems like music or creativity? And finally, am I okay joining a never-ending adventure? What we know about generative music is that even if we don't have its success metric, there's always room for improvement and for innovation. Just like we haven't extinguished creativity in music, even though like we've been active with music for thousands of years as a human species, still we're not going to finish, we're not going to end research in generative music anytime soon, because there's always going to be more to learn, more to research, and more to innovate. But then, if you answer yes to all of these questions, then probably generative music is something that you may want to consider pursuing for your career as a researcher, perhaps as an engineer. Cool. So this was the presentation. Now I just want to leave you with a few kind of like markers and links to find my work. So if you want to learn more on AI, audio, and music, I have like my channel that's called The Sound of AI. I'll briefly show this to you guys. Okay, and as you can see here, I have like a lot of like different courses and series on deep learning for audio signal processing, and I just finished very recently generating sound with neural networks, so just like using variational autoencoders for generating sound. And there's a lot also like to learn from the perspective of companies, or if you want to get started with these careers, tips and tricks. This is a whole series dedicated to that. Okay, then another thing that I would highly suggest you like to check out is the Sound of AI Slack community. This is the community behind the open source research project, and here we have fully dedicated Slack with more than 2,000 people active on it. And of course, I want to leave you with this call to action, which is guys, please help us out annotating this fantastic data set that's going to also help out the whole generative music community. And if you do want to spend a little bit of time helping like an open source research project, you can just like come here, and then you will be able like to annotate and help us like with this cool project. Cool. And here you have like all of my other links if you want to send me, like, for example, an email, or if you want to follow me on Twitter or LinkedIn. Okay, yeah, that's it, guys. So let's open it to questions if there are any.
Thank you, Valerio. That was very interesting. I'm sure everyone enjoyed your talk. So now is the time for the questions. Well, guys, if you have any questions or doubts you'd like to ask Valerio, just type them on the chat and I read them. I've seen that there are already some, so I'm gonna start with the first one. So the first question is, how did Melodrive learn? Did you base its output on human annotation of emotion? Did visual input play part in the decision of its generative process?
So I have to say that I'm no longer part of the Melodrive project, so I can't really tell much about that. But some of the things that we shared publicly about it is that we indeed had kind of like a mixed approach where we had some learning directly from music and in different styles. And then we had a lot of also kind of expert-based or rule-based systems on top of that. So we had these two processes combined. So some coming from machine learning and some coming from a more I would say music theory and rule-based approaches. This is something that we learned, and it's something that it took us quite some time to realize that it's really not possible to have an algorithm that rules them all, in a sense. You should use multiple algorithms together, and different algorithms will be good at different tasks. For example, for generating chords, you may need a certain type of algorithm, but for generating melody on top of those chords, you may need another type of algorithm or approach, if you will. And this is something like that. It took us some time, experimentation, but now I'm a firm believer that in order to create a very good generative music system, you have to have a very hybrid approach and multifactorial, taking into consideration different algorithms, different representations, and just like that.
Okay, thank you. And there's another question, which is, how do you think classification algorithms created by big tech will reshape perception and production of music? Do you feel like the simple modules used for emotion could diminish quality?
Okay, so I think the algorithms built by big tech are quite a big push overall, in generative music. And the main reason is not necessarily because of the algorithms themselves, but because of the interest that they raised around this topic. I mean, generative music is very niche, right, as a field or subfield of computational creativity. Now, a lot of attention was drawn to it through these algorithms, like the Jukebox algorithm by OpenAI, Music VAE, and the Magenta project. So I think they may work as catalysts in order for other researchers to pick up those ideas and then implement them. Now, I don't know if the revolution, the generative music revolution, will come from big tech or startups, companies, but I would guess that probably will come from the latter, so from startup companies, because you need a completely disruptive idea, not necessarily disruptive technology, but also idea and product idea, because the technology more or less is there for many use cases, kind of functional music and stuff like that, but I don't see so far any companies that have really cracked the product problem or the product market fit. So we have the technology, but we don't have a market that really wants to use that technology already.
Okay, and the next question is, in your opinion, what are the potentialities for granular synthesis in music generation algorithms?
Yeah, I think like that's an interesting question. So I would say like there's a lot in terms of like synthesizer that is going to happen with machine learning. And I showed you like a couple of examples. So one is NSynth by the guys at Magenta, but also like the open source research projects. So synthesizers are going to be revolutionized by machine learning. So we're going to have like neural net synthesizers, and these are going to create like some crazy sounds, and they already had, to be honest. In terms of like granular synthesis, I think like there's a possibility to apply machine learning to granular synthesis as well. And I think like that is also like a perfect recipe to create even crazier sounds, like combining approaches that from DSP as well as from machine learning together. It has worked already for a bunch of like different tasks in generative music and sound generation, and probably will work also for granular synthesis. Yeah.
Okay, thank you. Now there is a more technical question, I would say. So I've recently trained a transformer model to generate pieces of music in different genres of heavy metal. Very convincing. What do you think about transformers for symbolic conditional generation of music?
Yeah, I think transformers are the way ahead, most likely. But as I said, I don't believe that we're going to have just one model that's going to like rule them all. So, because from my research and my understanding of the space, representation in a sense is as important as the models that you use for generating music. If you don't have a strong representation of the music, you're going to have a quite weak way of controlling the music itself. Try to explain myself there. So, I mean that the models should know about the different music like elements, segments that you have there. It's very important that the model be aware of harmony, be aware of rhythm, be aware of the musical structure at different levels of resolution of the musical hierarchical structure. In that sense, I believe that a single machine learning model may create some impressive music on and by the way, it's already doing this. Like many of these transformers are creating like quite impressive music already, but on a very short time span. For having like music direction, probably you will need to have like this kind of like higher level understanding of the different musical aspects, the different music factors built into the model, and then potentially use different models for different tasks. To go back to the specific question asked, I think that, as I said, transformers will be the way ahead in many fields of symbolic music generation as well, not just like array audio generation. I think for many tasks there could be overkill, because simple LSTM could just work fine for that. But for most complex tasks, they will definitely like boost them as well.
Okay, so the next one is, could you elaborate a little more on the difference between raw audio generation and symbolic audio generation?
Okay, so raw audio generation and symbolic music generation. And I mean, so you would say like that you do like generation of music, but in the raw audio domain. So what I mean by that is that you can represent music in a bunch of different ways, right? So, and these are ways that are kind of like palatable for machines. So machines can understand that representation. So the raw audio aspects is basically just using a waveform. So you use the waveform representation of a signal, and you pass that directly to a machine learning model. The machine learning model, hopefully, is going to learn all the patterns within that raw audio representation of the music, or in other words, that wave file, right? But that is a very high dimensional space because there's a lot of data points. So you have these sequences that are huge. So say, for example, like in a CD, every 1 second worth of music has more than 40,000 points. So it's a huge, humongous sequence. So this is like very difficult for a machine learning algorithm like to learn. And so one of the advancements like in raw audio generation of music was done through, for example, like with OpenAI, was done by trying to understand higher level, hierarchical like representations like of this sequence with a lot of dots, right? Whereas when we're talking about symbolic music generation, we're representing music in a different way. We're representing music which notes as we know them, like from music classes. So you have a score, you have your pentagram, you can put like a bunch of different notes there. Each note has a duration, it has a pitch, and that is like a symbolic way of representing music because we are using symbols to map musical events. Now, the great thing about symbolic representation is that it's way lower dimensional than audio, audio representation, because you can express, for example, a melody that's long, I don't know, like 20 seconds of a melody, which a few notes, and that's it, okay? So you are comparing like a few data points in a sequence against hundreds and hundreds of thousands of points. And this is a huge advantage. The problem that comes with symbolic music representation, though, is that it completely ignores the level of timbre and the level of performance, because it doesn't have any information about the sound itself. It only has information about pitch, duration, perhaps the level of loudness, like the level of like volume that you want there, and that's it. And so on the one hand, raw audio representation is great because it gives you this extra information, which is that of timbre and that of like expression dynamics as well as performance. But on the other hand, it has this drawback, which is like highly computationally heavy. But if you compare that with symbolic representation of music, you have like the opposite, really. So you have like a way more constrained, way lighter representation of music, but you lose a lot of information there. So in a nutshell, like this is the kind of like difference between these two representations and like their pros and cons.
Okay, thanks. Then the next one is, how do you map emotions from visual inputs to music audio features? In other words, how do you define if a happy image is high in tempo, energy, valence, etc.?
Okay, this is a fantastic question. In our case at MeloDrive, we were completely ignoring that problem because we had an API, an SDK, which indie developers or game developers could use to tell the system the valence in the arousal, so the energy level in the kind of like positivity and negativity that you would have in terms of like feeling of the experience like of the game in that precise moment. So we weren't really mapping emotion from visuals to music, but rather asking the developers to give us information about emotion directly. So in that sense, like we weren't doing that. Now, if you're asking how you map emotion from how can you map like different emotions into music, that's a whole like other questions. And here there's a lot of research like on that aspect. And you'll see quite a lot of like literature trying to outline how you can map like different musical aspects onto like different emotions. For example, like I'll give you an example that's like quite simple and like overused perhaps, which is mapping, for example, major chords to happy or like positive valence feelings or emotions, like happy, tender, whereas like minor chords towards like negative valence, so sad emotion or things like that, or angry, stuff like that. And then you can also map different types of musical factors to emotions. Say, for example, you consider tempo. So high tempo, so music which is very quick, speedy, is usually mapped to high energy emotions, like being super happy, super excited, or super angry, for example, right? Whereas if you have emotions, or if you have like music that's very low tempo, like for example, ambient music that is way calmer, it could be calmer if it's a positive valence type of emotional music, but it could also be sad, because in sad we don't have a lot of energy, but we have like negative valence. And so there are like many of these tricks that you can use to like map different emotions onto like different, or I should say like the other way around, different musical factors onto different musical emotions, and try to entail like those emotions. Now, there's also like another aspect that I find quite interesting, which is having the machine learning all of these musical factors from music directly. So if you have a lot of music and you have good annotation for that music in terms of like emotional annotation, valence, arousal, so you can try to extract different musical features and understand, or let the machine understand automatically how different musical factors affect the perceived emotion of a musical passage.
Okay, so now Pilviosol asks, have you ever used transfer learning for generating music from already trained variational encoder models? Is it possible to produce quality results with few training samples?
Yeah, this is a quite good question. Yes, I did use transfer learning in the case of like variational autoencoders, but I mean the results. So the problem is like the for example, like the models, how were like the models trained in the first place, on what data set, for example, on which data, right? And if you have like data that's not very like generalized, then you'll be, even if you use the transfer learning, you'll be kind of like bound to like very constrained like musical output. So I would say like it's still quite difficult to use transfer learning effectively for generating music, starting from very few examples. So at least like this is like my experience with it. So, and most of the time you'll have that to build your own data set, or if you're lucky, working on a use case that has been already covered by other researchers or industry experts, then you may rely on other data sets that you find out there. But I would say, yeah, transfer learning is a possibility, but it hasn't really been studied to its full potential in generative music yet, given the huge variability that you have like with generative music. Because you may have like a generative music system that only focuses on folk songs, generation of voice folk songs, right? Another system that was trained on piano, monophonic piano melodies, or classical music piano pieces. And so you can't really like reuse that for other purposes. In that respect, this is something that's still to be like discovered and pushed more in terms of research.
Okay, then there is one last question, which is, for anyone starting out with AI for music, what courses can they get started with to learn on your own? And from where can one learn that?
Okay, yeah, of course. I have a YouTube channel for that, and it's called The Sound of the Eye, so you can just go check that out. And there I have a lot of series that you can check out for kind of like self-contained series for deep learning, for audio signal processing, generative music and all of this kind of stuff. I mean, the process is quite difficult because it's not really well structured. So this is something that's kind of like picking up right now, and it's getting a lot of hype like right now, but you really don't have like many, for example, university courses that cover these things, right? Or university degrees. So the thing that I would suggest is, well, apart from like going to the Sound of AI channel and the Sound of AI community, because there you can ask a lot of questions and get feedback from other people at different levels of expertise. The other thing that I can suggest is just like to be curious, go to the papers, read blogs a lot, and be just like up to date with all the research that people like put out. Probably at the beginning, you absolutely will won't have the skills or the kind of the ability to learn and understand many of the things that researchers like will publish, but still like get an idea, get a taste for it. And then start from the basics, start from artificial intelligence, start from digital signal processing. If you're not a musician, get familiar with music theory, music cognition, this kind of stuff, and then start experimenting with simple projects. Generate, for example, a simple melody using an evolutionary algorithm, or use your first LSTM to generate a chord sequence, stuff like that. You start with things that are simple, and then you make them ever more complex. And then this one like is a kind of like very new, but I'm currently working on a course that basically like sets out like a way of like building like your career in AI audio with all of its different specialization, like from music information retrieval to speech processing to generative music. So yeah, stay tuned for announcements like and updates on that as well.
Okay, another question just came. I feel like a big part of working with machine learning is asking the right questions. Do you have an approach for finding a way to ask the right questions?
Well, this is like a very, very good, this is good insight, right? So it really depends on what you're working. I mean, if you are working in generative music, so I would say like the questions are like quite simple, that you should ask like a quite simple in a sense, right? And a way to also ask the right question is understanding like the complexity of music, having like a very good understanding of, for example, like musical structure, or musical form, or different like characteristics or musical factors and how they contribute together to create like very complex pieces. And so having a very good understanding of that aspect, the kind of like theoretical music theory aspects behind music is instrumental to also ask the right question for using machine learning in generative music. But where I think machine learning needs to have like the most precise, most insightful questions is in music information retrieval, where there's a lot of variability there. For example, if you want to train a generative, not a generative, but a genre music classifier, like, for example, like some of these algorithms have been like also developed by Spotify and similar tech companies, right? So you listen to a lot of music and then you say, okay, yeah, so this is hip hop, this is, I don't know, progressive rock, or this is classical music, right? And there it's very important that, again, you have very good understanding of what you're talking about. Because you may end up like asking very stupid questions, like for example, having a genre music classifier that has like a genre taxonomy that's too simplistic. For example, many genre datasets, you have only like 10 different genres, which makes absolutely no sense, and it's nowhere near what's like able to capture the complexity of music in a real world scenario. And so you need to have a very good understanding, like of, in this case, like of genre, and how to create like a taxonomy of different genres and styles like that makes sense. And then use that information to inform your taxonomy and your data sets, therefore informing your machine learning processes and training. So my advice would be always know the theory behind what you want to do on the music side. And this is not just for music, but also for speech and other types of like audio signals, like noise, sound, stuff like that. You really need to have a good understanding like of audio signals or speech processing, digital signal processing, in order to really just go beyond the simple black box approach. Okay, because now, like with machine learning, people think, okay, yeah, so I have a ton of data, I'll just feed that to a neural network and then it'll figure out by itself. Well, no, it's not going to happen like that. Well, it can happen if you're playing around with a tight data set. Yes, of course, for a university project, that's perfectly fine. But then the moment you step out of your comfort zone and you start building projects in the real world, well, you need to have a perfect understanding of all of the variables at the contour, like at the outside, at the outskirts, like of what you're trying to do.
Okay, then, if nobody has further questions, we can conclude this talk. Thank you again, Valerio, for coming here today. We really appreciated your speech, and thank you all for following.
Thanks a lot.
Goodbye.
For the invitation. Cheers.
Goodbye, everyone, and see you next talk.